Chapter 6. In beginning, we have an image from our book, which kind of walks you through the amount of processing that actually has to go into compiling a CT image or scan. First, we begin with CT detectors, which is something that we all probably realize actually occurs. And then we go into pre-processing. Then from pre-processing, we actually come up with reformatted raw data. It's in this raw data that we apply things like filters and algorithms, which help to enhance our images and allow us to have something that is both diagnostic and excellent in quality. And then we actually have our reconstructed images. From these reconstructed images, then we can just choose to store them, display them, record them onto alternative media, or archive them for future reference. So if we begin by looking at the basic principles, we come to the conclusion that for the computer to reconstruct an image of the patient by CT, the X-ray tube and detectors must rotate around the patient at least 180 degrees. We need to circle this because regardless of what type of scanner that we actually use, 180 degrees will actually come into play. However, we do know that helical scanners or volume scanners, now multi-slice, can rotate over 180 degrees and typically can go 360 degrees, which allows us to understand why they are called helical scanners. If you'll remember back, the 180 degrees or a half of a turn would actually cause the tube to become coiled, to become tangled up in the coil or of the wire, and so the wire would have to be uncoiled, and then the scanning would resume. However, we're not limited by that today, and so we can have 360 degree tube rotation, and this allows us to see that they generate better quality images simply because of being able to rotate and have faster scan times. So if we refer back to the second bullet point now, we see that the reconstruction process is based on the use of an algorithm that uses the attenuation data measured by the detectors to systematically build up the image for viewing and interpretation. So basically, as we saw with the previous image, we take what is measured by the detectors and then build this up into a reproducible image. So one of the ways that we actually compile these images and make them diagnostic in quality is through the use of algorithms. We typically think of algorithms solely being in the modern technology age. However, a quick examination will allow us to see that there have been many uses of algorithms throughout history. We see in radon in 1917 actually used an algorithm in terms of researching the theory of gravity. Bracewell used it for astronomy, and then we have electron microscopy, optics, and then we get into medicine. And so we see that there have been several uses of algorithms, such as Ohlendorf, Kuhl and Edwards, Cormack, Bates and Peters, and then someone that we're very familiar with is Hounsfield in 1971. And so we'll examine the use of Hounsfield's algorithms and how there was need for improvement. So throughout the use of modern day technology, we know that algorithms are utilized, but many times we fail to realize that algorithms are utilized in radiology, in imaging, and non-imaging applications. So we commonly encounter algorithms throughout our daily job. However, we just fail to realize that. So what exactly is an algorithm? An algorithm is a set of rules or directions for getting a specific output from a specific input. And so, basically, one simplistic version of an algorithm would be y equals 5 plus x. And so you put in a specific input and you get a specific output simply by this equation. And so basically what this equation tells us is that whatever you have for x, you have to add 5 to it to get y. And so that is a set of specific rules. And so the distinguishing feature of an algorithm is that all vagueness must be eliminated. The rules must describe operations that are so simple and well defined that they can be executed by a machine. And so basically we have to understand that a computer uses artificial intelligence, which requires that there be an operator to actually tell the computer what to do. And so the algorithm functions in that sense to become the operator to tell the computer what to do from a specific input. But it has to be so simplistic that the computer can actually carry it out. So that brings us to the Fourier transform. The Fourier transform is widely used in science and engineering, and it's a useful analytical tool in mathematics, astronomy and chemistry, physics, medicine, and even radiology. In radiology, the Fourier transform is used to reconstruct images of patients' anatomy in CT and also in magnetic resonance imaging. However, as we'll see, it's not widely used in CT simply because of the fact that it is very tedious and it takes an enormous amount of mathematical skill to actually carry this out. Okay, an analogy between the Fourier transform and hearing. Incoming sound waves that enter the ear are separated into different signals and intensities. And we can all understand this because we have high frequency, low frequency, and these signals then arrive at the brain and are rearranged to produce a perception of their original sound. So basically what we're saying here is that the ear separates these small little differences in the sound in terms of intensity, and then it relays this information to the brain, where the brain then compiles everything back together and makes something different out of it. And so you actually wind up perceiving the original sound. The Fourier transform is a function that describes the amplitude and phases of each sinusoid, which correspond to a specific frequency. In other words, the Fourier transform is a mathematical function that converts a signal in the spatial domain to a signal in the frequency domain. And so basically, just as your ear hears all of these sounds and then separates them in terms of intensity, the Fourier transform does much the same thing, where it separates different wavelengths and frequencies of the X-ray beam. And then basically what it does is it divides it into a series of sine and cosine functions of different frequencies and amplitudes, and these can then be separated, much like the ear does, and then compiled back together with various parts augmented. We also have interpolation, and you'll probably want to put a star by this because you will see interpolation in when we actually move into the multi-slice CT algorithms. Interpolation is used in CT in the image reconstruction process and the determination of slices and spiral helical CT imaging. Interpolation is a mathematical technique to estimate the value of a function from known values on either side of the function. In short, data from the tube rotations just above and below a given slice position are used for image reconstruction. And it allows for the reconstruction of a thin, motion-free image from a volumetric data set acquired from a moving patient. And so basically, what it allows you to do is take the information that you acquired while you're going through the helical process and compile it all, and so that you can single out one small spot of information. And basically, when we're talking about uses data from above and below, it would be like this. We have a line, and 1 and 3 are at the end of it. So if I told you that 1 and 3 were at the ends of this line, then it would be easy to hypothesize what the center would actually be. We would know that it would be 2. And so basically what you're doing is you're taking measurements from above and below and using that to predict what should be in the center. And that's much the same way that interpolation actually works. So that brings us to convolution. Convolution is a fancy way of saying that we use a filter. Okay, so you can think of convolution and filters being like this. That if you were brewing coffee and you were using ground coffee and you wanted to brew the coffee without actually having coffee inside of your coffee, if that makes any sense. Basically, if you didn't want any remnants of the coffee, you just wanted the flavor of the water, then what you would use is a coffee filter. If you didn't have the coffee filter and you just dumped it into your machine, then you would get coffee flavored water, obviously, but then you would also get coffee in its ground form in your drink. And so while that would be very unpleasant because you don't have a filter, if you simply used a filter, you would get all of the taste and the caffeine from the coffee, but you wouldn't actually have ground shards of coffee inside your drink. And so that's much the same way that convolution or a filter actually works. Convolution is a digital image processing technique to modify images through a filter function. And so basically, it's charged with cleaning up the images. And we'll see that actually applied to some of our algorithms. The second bullet point says the process involves multiplication of overlapping portions of the filter function and the detector response curve selectively to produce a third function, which is used for image reconstruction. Basically, you can really not worry about that. Sometimes our book gets in a very, very in-depth discussion of things. So, image reconstruction from projections. How do we actually build up an image? In his initial work, Hounsfield's images were noisy, and that was a result of his chosen reconstruction technique. If we'll recall back to the first lecture, we saw Hounsfield's initial image and or sample of his initial image, and it was unlike what we see today in terms of being clear and defined. It had tons of noise, and that was simply because of his reconstruction technique. So basically, to remedy this, special algorithms such as convolution back algorithms were soon introduced. And so that is more along the lines of what we use today. And more specifically, what was probably introduced before this was back projection algorithms. And we'll see what these are in just a few moments. These algorithms were developed in 1971 and 1974 to help improve image quality, and not only image quality, but processing time. So that if you can reduce the amount of time that the computer takes to actually process the data, you will ultimately be more effective. And that's what we see even today. So basically, there were 3 types of reconstruction algorithms that were initially constructed. The first is back projection. The second is iterative methods. And then the third is analytic methods. And we'll see that analytic methods are what we typically use today for several reasons. So if we first begin by looking at back projection, we have to understand that back projection is simple. It uses simple mathematics that really doesn't require a complex understanding. It's also called the summation method that we see here, or the linear superposition method. So the way the book actually defines it is, if you consider 4 beams of X-rays that pass through an unknown object to produce 4 projection profiles, you're going to see that you have P1, P2, P3, P4. These are going to become back projected to form a corresponding image. And so basically what you're going to see is a result of back projecting these images onto a matrix. And the problem with this, and this is something that you need to put a star by both of these bullet points. The problem with this is that back projection technique does not produce a sharp image. That's one of the things that we strive for in terms of CT, is producing sharp images that are excellent in diagnostic quality, and back projection simply does not do that. And so the ultimate thing is that it's not used in clinical CT. Additionally, the most striking artifact of back projection is the typical star pattern that occurs because points outside a high density object receive some of the back projected density of that object. And so basically, if you're supposed to have something that looks like this, then you're going to have something that looks like this. And so you're going to have all of this excess data or noise, and your resulting image is not going to be sharp at all. And so here we ultimately see what we're looking for in back projection. We have the object here, and we can see that we have a dot in the center. If we produce X-rays that are going this way, and then going this way, and even going vertically through this object, we get something that looks like this. And so as you can see, there is a dot on the inside, but there's also a lot of excess noise. And so the result of this is that we have an unsharp image. So ultimately, this resultant lack of sharpness proves to be no longer useful in producing a computer tomography image. This brings us to iterative algorithms. So, an iterative reconstruction starts with the assumption that all points of the matrix have the same value, and compares this assumption with the measured values, makes corrections to bring the two into agreement, and then repeats this process over and over until the assumed and measured values are the same or within acceptable limits. Techniques of this include simultaneous iterative reconstruction, the iterative least squares technique, and the algebraic reconstruction technique. These techniques differ in the application of corrections of subsequent iterations, and we see that the algebraic reconstruction technique was used by Hounsfield in the first EMI brain scanner. So what I've highlighted is something that you want to take note of in your notes. Today these techniques are not used in commercial scanners because of the following. Number one, it's difficult to obtain accurate ray sums because of quantum, noise, and patient motion. So basically, it's inaccurate. That's one of the things that we do not want. We want accuracy, and we strive to differentiate ourselves from inaccuracy. Also, the procedure takes too long, so we see that it takes too long to generate the reconstructed image, because the iteration can be done only after the projection, after all of the projection data sets have been obtained. And so basically you would have to wait till the end of the scan to actually see one image. And to produce a true image, there should be more projection data sets than pixels. Therefore, diagonal projection data sets are taken to eliminate ambiguity. We're not going to worry too much about this third bullet point, but definitely know points 1 and 2 as the reason why we don't actually use iterative methods any longer. So that brings us to analytic reconstruction algorithms. Analytic reconstruction algorithms were developed to overcome the limitations of back projection and iterative algorithms and are used in modern CT scanners. So that's something that we want to take note of, that they're used in modern CT scanners. So when you think of modern CT, you think of analytic reconstruction. Two analytic reconstruction algorithms are the Fourier Reconstruction algorithm and the filtered back projection. We will see that only one of these is actually utilized today. So if we begin by filtered back projection, we see that filtered back projection is also referred to as the convolution method. Once again, remember that filter and convolution are, speaking of, very much the same thing. The projection profile is filtered or convoluted to remove the typical star-like blurring that is characteristic of the simple back projection technique. So what we're striving to do here is to remove the star pattern and only see the images that we need. So this is what we're striving for here. The steps in the filtered back projection method are as follows. All projection profiles are obtained. The logarithm of the data is obtained. The logarithmic values are multiplied by a digital filter or convolution filter in order to generate a set of filtered profiles. The filter profiles are then back projected, and the filter projections are summed, and the negative and positive components are therefore cancelled, which produces an image free of blurring. And so you really don't have to understand these steps 1 through 4, but what you need to understand is that ultimately this produces an image free of blurring. So Fourier reconstruction. The Fourier reconstruction process is used in MRI, not in modern CT scanners. So that's something that you need to keep in mind. It's not utilized in modern CT, which we typically use filter back projections and kind of a modification of those. It requires much more complicated mathematics than does filter back projection algorithms. So it's very much more complex to yield the same results. A radiograph can be considered an image in the spatial domain, that is shades of gray, represents parts of the anatomy, such as bone is white, air is black, and it exists in space. With the Fourier transformation, spatial domain image, the radiograph represented by the function x of x and y can be retransformed into a frequency domain image represented by the function f of u of v. So there are several advantages to this transformation process. The image in the frequency domain can be manipulated, such as edge enhancement or smoothing can be applied by changing the amplitudes of the y component. So very simple. Second, on a computer can perform those manipulations. And third, frequency information can be measured, can measure image quality through the point spread function, line spread function, and modulation transfer function. So we see that there are benefits. However, all of these benefits are negated because of the amount of time it takes to utilize this process and its complexity. And so basically, because Fourier reconstruction is so complex and requires advanced mathematics, then it really is not beneficial for what we're attempting to do in terms of CT. So we don't use Fourier reconstruction. So here we see this diagram. We have back projection. Then we have the filter, and then we have filtered back projection. So basically, filter back projection without the filter is still back projection. So if we look at the image, where we should see a profile that looks something like this in terms of a square or a rectangle, we see that we have a star pattern simply because of the back projection. However, if we apply a filter to it and pass it through the filter, then we now have what we were actually supposed to see, which is a square. And that's simply because of the use of a filter. And so that's why it's essential for us to have filtered back projection when using CT. So the image reconstruction in single slice spiral helical CT. The image reconstruction algorithms previously described apply to slice-by-slice conventional CT, which we know as the stop-go motion of conventional CT. In a single-slice spiral helical CT, the same filtered back projection algorithm is used with an additional consideration. And this is a result of the patient moving continuously through the gantry for 360 degrees of rotation. The reconstructed image has a tendency to be blurred, and so as we know, that's because as the tube is rotating, the patient is actually moving, and so there would have to be blur simply as a result of the patient moving on the table. The reconstructed image is going to be blurred, and we have to utilize interpolation before filter back projection, and so we use interpolation before filter back projection. However, that is for single slice helical CT. When we enter into multi-slice spiral or helical CT, we see that it even becomes more complex. In general, for CT scanners with 4 detector rows, and that's something that we need to keep in mind for 4 detector rows, multi-slice CT algorithms have been developed to allow for reconstruction of variable slice thicknesses and address the problems of increased volume coverage and speed of the patient table. This is made possible by the spiral helical scanning with interlaced sampling, longitudinal interpolation, and fan beam reconstruction with the filter back projection algorithm. The new generation of multi-slice CT scanners, those with 16 and greater detector rows, require modified image reconstruction algorithms. However, the book is very forthcoming, and we see that these algorithms are so advanced that they even extend beyond the scope of this book. Multi-slice CT scanners with 4 detector rows use a wider fan beam geometry compared with single-slice CT, and therefore use a 2D reconstruction with interpolation and Z-filtering known as Z-interpolation algorithms. The algorithms for single-slice and multi-slice CT with 4 detector rows are referred to as spiral helical fan beam approximation algorithms, simply because they're based on fan beam geometry. And basically, this approximation algorithm assumes that the source, detector, slice of interest all lie in the same plane, and that the projection of the slice of interest falls on a single row of detector. And so basically, what we have to look at is this presumes that the X-ray beam is going to fall on one single row of detectors. However, it's only valid for small cone angles associated with 1 to 4 slice systems. As we increase the detector rows, then we increase the amount of cone angle. And as we'll see, this causes us to need further algorithms. So cone beam geometry. For a 4 detector row multi-slice CT scanner, the beam divergence from the X-ray tube to the outer edges of the detectors increases, and such a beam is called a cone beam. Within the cone beam, the rays that will be measured by the detectors are tilted at an angle relatively to the central plane or perpendicular to the long axis of the patient. This angle is called the cone angle. And so basically, if we try and draw a crude rudimentary drawing here, we have the tube, and then as we see, we have something that looks like this. And as you can see, it kind of has a pyramid shape, and that's what we call a cone. And so basically, the more rows of detectors you have, the more or the larger the cone is going to be, and the greater the angle. And so basically, it's going to keep stretching and stretching and stretching until it hits multiple detectors. So as the number of detector rows increases from 4 to 16 to even 64, the cone angle becomes very large. The larger the cone angle causes problems where the beam divergence along the z-axis becomes greater. This will result in the plane of interest being projected onto several detector rows. So basically, you have one row, another row, let's redraw that. If you have one row, 2 rows, 3 rows, 4 rows, and you have an angle coming in we see that it could strike multiple detector rows, projecting some of the data for one onto another. And we see that this generates inconsistent data that will lead to artifacts called cone beam artifacts, such as streaking and density changes, both of which will have a negative impact on image quality. So basically, it generates inconsistent data or inconsistent images, which is something that we strive to distance ourselves from. So we find that fan beam approximation algorithms require that the data be consistent. That is, the X-ray beam from the tube to the detectors and the section being imaged must be in the same plane. And so it requires that there be no overlap or no projection onto another detector. And so we use cone beam algorithms. Basically, they fall into 2 classes. We have exact cone beam algorithms and approximate cone beam algorithms. We need to know nothing more than just these 2 algorithms exist. So just highlight this and know that these are 2 algorithms that we use. So we also find that there are different types of data in terms of CT, and depending on what process it's in will depend on what type of data it is. There are 4 types of data. There's measurement data, raw data, filtered raw data or convoluted data, image data or reconstructed data. So if we first begin by looking at measurement data, we see that this is scan data. This is what comes from the detectors. This is data that is in a numeric form on a matrix. This data set is subject to pre-processing to correct the measurement data before the image reconstruction algorithm is even applied. Such corrections are necessary because of errors in the measurement data from beam hardening, adjustments for bad detector readings, or scattered radiation. If these errors are not corrected, they will result in poor image quality and generate image artifacts. So this is our first step where some of the data is actually corrected. But if you'll remember, the image that we see on CT is not how the data is always presented. Initially, the data is acquired in numerical form, and that's what this is actually talking about. This is the raw measurement data. That brings us to raw data. Raw data are the results of pre-processed scan data and are the subject and are subjected to the image reconstruction algorithm used by the scanner. So this is after it is converted from a numerical form, and we have the data in an image form, and it's going to be pre-processed with some of the algorithms used, so it cleans it up so you don't have this messy looking image. Then that brings us to convoluted. This is supposed to be convoluted. We see that the image reconstruction algorithm used by current CT scanners is filter back projection, which includes both filtering and back projection. The raw data must first be filtered with a mathematical filter or a kernel. This is referred to as the convolution technique. Convolution improves image quality by removing blur. And so, as we saw before, it helps to remove the blur due to the fact that the table is moving with the patient, and it helps to basically clean up the image. The important thing to notice is that convolution kernels can only be applied to the raw data. Once the data is transformed from raw to convoluted, you cannot go back and change this. So here's an idea of what the filtering process actually does. Here you have one image without a filter and the other image with a filter. And so, as you can see, the one without the filter has a very haziness appearance. You do see the inside of the circle, but you don't really see a clear definition. If you apply the filter, then you get a uniform density all across. And as we can see, the graph kind of demonstrates that in itself. As we can see, the graph kind of has a curved shape, meaning here is the most densest, and as we can see here, it's equal density throughout. And so this filter does a remarkable job of improving image quality. That brings us to image data. Image data, or reconstructed data, is convoluted data that has been back projected into the image matrix that CT images are displayed on a monitor. Various digital filters are available to suppress noise and improve detail. The standard algorithm is usually used before the previous algorithms, especially when a balance between image noise and image detail is mandatory. And so basically, to the image data, we can apply algorithms as well. And these digital filters seek to enhance certain parts of the image. Smoothing algorithms reduce image noise and show good soft tissue anatomy. They're used in examinations where soft tissue discrimination is important to visualize very low contrast structures. Edge enhancement, on the other hand, emphasize the edges of structures and improve detail but create image noise. They're used in examinations in which fine detail is important, such as the inner ear, bone sutures, thin slice, and fine pulmonary structures. So as you can see, the edge enhancement is what sometimes is referred to as detail, because it is tasked with focusing on details, while the smoothing algorithms tend to smooth everything out and provide a uniform appearance. Here you can see the detail versus smooth. As you can see, the detail has tons of noise on the inside of the brain, whereas the smooth does not. But if you'll notice, we see clear differentiation in the skull, and at the posterior of the skull we do see scalp at the posterior portion, whereas on this image, image B, we do not see any. As you can see though, the smoothing tends to make the brain look more like a brain than an enhanced mess like the detail does. However, many people and many scanners usually go with the standard algorithm, which provides the best of the both worlds and really employs it for usage on things like this. So in our last slide, we just see the importance of everything. We have pre-processing, and then we have display. And so there's tons of steps that have to go in to actually get a displayed image, and these are just some of the few that we've talked about.